video is going to be on 1-4 arithmetic sequences and series. This will most likely be divided into two parts, with the first part dealing with sequences and then the second part dealing with series. A sequence is basically an expression that you're going to use to find the next term that would be in a sequence, whereas a series is typically a sum where you're adding up all the things that are in a particular sequence. This critique and explain, if this was something you were supposed to complete, it will be assigned either in class or in Savas Realize. So you don't have to worry about that for right now because that's something that has already been taken care of. So now we have our essential question for this section. What is an arithmetic sequence and how do you represent and find its terms and their sums? So the sum part of that is going to be where the series comes in. But we're going to look at two different ways that you can represent an arithmetic sequence. So your sequence is some function whose domain is the natural numbers, 1, 2, 3, 4, 5. The natural numbers are all positive integers, does not include 0. So this would be like the first term is this, the second term is this, the third term is this, the fourth term. So you're matching up whatever term you have in the sequence with then the number in the sequence. An arithmetic sequence is a sequence that has a constant difference between each term. Now, common difference, that doesn't always mean that we are subtracting. It just means that between each term in the sequence, you get the same value. So either you're consistently adding some number, you're consistently subtracting some number. It's the same number within your series of numbers. So the difference, we do represent it as a lowercase d, and you'll see that in the formulas that we use for this section. So example 1, we want to know if this sequence is arithmetic, and if so, what the common difference would be. And what is the next term in the sequence? So to find out if it is arithmetic, you want to see what the difference between terms is. So to go from 3 to 8, I would add 5. 8 to 13, I'd add 5. 13 to 18, I'd add 5. 18 to 23, I would add 5. That is consistent. So yes, this sequence is arithmetic. The common difference, that's that lowercase d, is 5. That's whatever you were adding or subtracting to get to the next term. The next term in the sequence then, if I add 5 to the last term, would be 28. So all three things there would come into play with this particular question. So now we're going to expand on this a little bit further. How could you write a formula for finding the next term in the sequence? So we're going to be using the same sequence of numbers from part A, but now we're going to find a formula. It doesn't always make sense to have to write every single term in the formula, so it's always good that we could predict the next one. So 4 n is equal to 1. My f of 1, this would be like my f of n, was 3. So the very first term in the sequence was 3. The second term in that sequence was 8. Now, how did we get that 8? Well, we took the first term and we added 3 to it. The third term, f of 3, was 13, making sure that I'm not using incorrect numbers here. Okay. That was the same thing as taking the second term, and see, I wrote a 3 up here. This should be 5. As I said in one of my other videos, this should probably make you feel like you're in class in live time, because sometimes my hand is writing faster than my brain is thinking. So we have f of 2 plus 5. So you're taking the second term which was the 8, and you're adding 5 to it, and that's how you get the third term. The fourth term for f of 4 was 18. And that was taking the third term and adding 5 to it. And you can see here then for the next term, that was 23, that was adding 5 to the previous term. So to come up with some type of formula for this, we are basically taking the previous term. So if we're finding f of n, you're taking the previous term and you are adding the 5 to it. So previous term and you are adding 5. There is a general rule for this, and you have to be careful with this particular type, because if you do not know where you're starting, if you don't know your f of 1, that can put you into quite a spot there. So this is your general rule. Notice it is a piecewise function. Your f of n is going to equal, you do have to state what f of 1 is. So this is always the first term. So you have to state what the first term is whenever you begin. And notice the first term exists when n is equal to 1. So that would be the very first term. Then you are going to have f of n, whatever term you're trying to find, is equal to the term right before it. So if I'm trying to find the 7th term, I need to know the 6th term. If I want to know the 20th term, I need the 19th term, plus the common difference. And this is for all the n's greater than 1. N is a positive integer. So n is not going to be decimals, and it's not going to be fractions, and it has to be the counting numbers that are bigger than 1, like 2, 3, 4, 5, 6. This is what we call the recursive definition. And you can see here, this definition is identical to what we had up here, except for instead of saying f of 1, I have this highlighted yellow a sub 1. A sub 1 stands for the first term, and this a notation is actually what we're going to be using in this section. D is still going to represent the common difference. Notice I highlighted that there. If you are subtracting to get to the next term, it would be minus that number instead of plus. So if the common difference was -3, it'd be a sub n minus 1 minus 3. The two highlighted things are the only things that are going to change in this. You're always going to have whatever your first term is. You're always going to have the n equals 1. Then you have a sub n minus 1. Again, this stands for the previous term with your common difference, and that's for n is greater than 1. This formula is extremely important. Extremely important. So this is, if you're writing down nothing else from these notes and from this video, please write this formula down. This is extremely important. So example 1c, is the sequence arithmetic? If so, write the recursive definition. Remember, recursive is that piecewise type function. So I want to look at my difference between terms, and I am adding 3 each time I'm going to the next term. So yes, this is arithmetic. My common difference is 3. My first term is 4. And you need both of those pieces of information in order to write the formula. So the formula for a sub n is equal to the first term, which is 4, and that's if n is equal to 1. And then it's equal to a sub n minus 1 plus 3 for all of the n's that are greater than 1. So this would all be part of your solution for that. So that's recursive. Now, recursive is not always going to be the best way to get the solution to problems like this, because especially if you're finding terms that are later on, like the 17th term, the 52nd term, the 139th term. It's not going to be helpful to have to find all the terms leading up to that term to just find the term you're looking for. And that's where our next formula comes in. The explicit definition is going to allow you to find any term in the sequence without knowing the previous term. So explicit definition, we can jump to whatever term we're looking for without having to know all the terms leading up to it. And that brings us to example 2a. Given the recursive definition, a sub n equals 3. Notice that's my starting term. If n is equal to 1, a sub n minus 1 plus 0.5, so 0.5 is my common difference, if n is greater than 1. We want to know what the explicit definition would be for the sequence. So let's start by writing out some terms. The first term, as we said, is 3. First term is 3. The second term, I would be adding the previous term, so the 3, and I'm going to add the 0.5 to that. Now I'm going to hold off on combining those together because I want you guys to see the formula that's going to emerge with this. And you won't see that if you automatically think 3.5. So just think about it as 3 plus 0.5. The third term would be the previous term, so the 3 plus 0.5 plus an additional 0.5. Well, now I have 2 0.5s, so that's the same thing as 3 plus 2 0.5s. The fourth term, I'm taking and adding another 0.5. So now I have 3 plus 3 0.5s. If I look at the fifth term, that's 3 plus an additional 0.5. So that's 3 plus 4 0.5s. You guys see the pattern that's going on here? When we were finding the second term, there was 1.5. When we were finding the third term, there are 2.5s. When we're finding the fourth term, there's 3.5s. When we're finding the fifth term, there's 4.5s. So if I was finding the 71st term, there would be 70.5s, which means that if I am finding the nth term, I am going to have whatever my initial term is, and I am going to have one less than the term I'm trying to find times that common difference. So again, if n is 32, I would have 31 of these d's, whatever this common difference is. So for this particular example, my first term was 3. So I'd have n minus 1 times 0.5. Again, the only things that I'm plugging in for, just like before, you're plugging in the a sub 1, and you're plugging in for the d. The a sub n and the n minus 1 are going to stay. It also doesn't matter which side of the parentheses you put the d on. You can put the d in front of the parentheses if you want. It's going to be exactly the same. This is another extremely important formula, and I don't actually have that on the next page. So if you have not already written this down, please write that formula down. And again, I'm going to scroll a little bit because my video is in the way of this. So this was our particular answer for this problem, but this is the formula that you would be using to answer any future questions. Okay, part B. Given the explicit definition, what is the recursive definition for the arithmetic sequence? So recursive and explicit both are going to be using the A1 and the D. So recursive, A1, does not look like a 1. A1 if n is equal to 1, and A, n minus 1 plus D for all n's greater than 1. So there's the recursive definition. The explicit definition is A1 plus, in this case, I'm going to do D times n minus 1 just because they have the number in front of the parentheses here. So if you can identify what number is in the A1 position and what number is in the D position, you can plug in for those same things over here. We can plug in there and we can plug in there. So if you look at this formula, what I have up here, it looks like my A1 is 16. My D in this case is a -3. So the recursive definition, I'm going to be plugging in the 16 for the A1, the -3 for the D. So AN is going to equal 16 if n is equal to 1, and AN minus 1 minus 3 if n is greater than 1. And that would be my formula there. You do not have to write plus -3. If you just write -3, that's perfectly acceptable for that type of question. Okay, the last one we're going to be looking at in this particular video. This example kind of puts this in perspective of a real-world situation. We have a high school auditorium that has 18 seats in the first row, 26 seats in the fifth row. The number of seats in each row forms an arithmetic sequence. So because it forms an arithmetic sequence, that means there is some consistent common difference. We want to know what the explicit definition for the sequence would be. So I know a couple of things. I know this 18 is going to be my A1. So I know A1 is equal to 18. This does not actually come out and tell me the common difference, so that is something that we will have to calculate. But I do know there are 26 seats in the fifth row, which means A sub 5 is equal to 26. So I can write an equation using this information and solve for D. Once I have D, then I can plug in to this formula. So I'm going to say my 26 is going to equal 18, which is my A1, plus my unknown common D times n minus 1. Well, since A sub 5 is 26, that means 5 is the particular n for this situation. So D times 5 minus 1. So I have 26 equals 18 plus 5 minus 1 is 4 times D is 4D. Subtract the 18. And you get that your common difference is 2. And I know for this situation, you guys might just go, well, I would just do 26 minus 18, and you have to go 4 extra rows, and so you divide by 4. That works out for this one, but if you do have a more complicated problem, especially one that has decimals in it, it's always a good idea to know the actual method for how to go through and solve this. So now that I know what my common difference is, I can take my common difference, and I can take my initial term, my first term, and plug into this formula. Again, I don't want to plug in the 26 and I don't want to plug in the 5 because I want to come up with some type of explicit definition that will allow me to find future values, which is actually what they're asking in part B. How many seats are in the 12th row? If I had plugged in the 26 and the 5, I wouldn't be able to answer this question. So in the 12th row, that means your n is going to equal 12. So I'm going to plug in n, or plug in 12 everywhere there's an n in this explicit definition. So A sub 12 is equal to 18 plus 2 times 12 minus 1. So this is 18 plus 12 minus 1 is 11. 11 times 2 is 22. So 18 plus 22 is 40. So there are 40 seats in the 12th row. That is going to do it for this video. In the next video, we're going to be looking at taking our sequences and adding up how many terms are in it. Maybe in this auditorium, it's nice to know how many seats are in each row, but you want to know the total number of seats in an auditorium because you're trying to figure out capacity for some type of event. So those are called series, and we'll do further work with them again coming up. Please let me know if you have any questions. You may have to do some studying to remember the difference between recursive and explicit. So it may just be something you have to commit to memory and go over. Just like with everything else that we do, please let me know if you have any questions on this section.